Work being done on an object only happens if there's a force acting on the object. And that force is either going to, make it move in a positive direction or it's going to hinder it in a negative direction. Work is also defined as a change in energy. So just like question number 1, where you have to find the change in potential energy, a change in something, a change in velocity, a change in acceleration, a change in force is always the final component minus the initial component. And in this case, it's the final energy minus the initial energy. Okay, so at this point, we've learned this. Work is equal to force times distance times cos theta. That's what we learned in the first lesson. Now we're going to learn that work is also equal to the change in energy. And we call this a work energy theorem. And so work is done when there's a change in any type of energy. Potential energy, elastic energy, kinetic energy, thermal energy, chemical energy. Any change in energy. So work done against gravity if there's a change in gravitational potential energy. There's work done if there's a change in an object's speed. That's kinetic energy. A work is done on a spring if it has a change in elastic potential energy. We call that ES. To differentiate between this EP here and this EP here, we leave this one. Sometimes you can see this written as capital GEP for gravitational potential energy. Not often. I have seen it. And this one we typically write as ES. Okay? Just so you're aware that you can see it in multiple different ways, but it means the same thing. So we've learned about the elastic potential energy in springs, but we haven't really looked at gravitational potential energy and kinetic energy. In fact, we haven't really looked at those since grade 8 when we were looking at mechanical energy. So it's been a really long time since we've looked at those. Kinetic energy is the energy of an object in motion. Kinetic, right? Kinematics was the study of objects in motion. Kinetic energy is the energy of an object in motion. And so this is how we solve for it. 1/2 times the mass times velocity squared. Well, that sure looks an awful lot like what other formula we just learned. It sure looks like this. And yet we call that spring potential energy. So this is an object in motion because we're looking at the velocity. Okay? Gravitational potential energy is when a mass is at a vertical distance. It has the ability to fall. So that's our questions here, where we have the guy with the ball at the edge of a cliff. Before this ball drops from his hand, this ball is 100% sitting at gravitational potential energy. It has the potential to fall. And we solve that by mass times gravity times the height that the object is at. Okay? So 2 new formulas. One's a review. We have seen these, just not for a very long time. And then we learned this one in last lesson. Okay? All right. We've seen a couple different types of potential energy now. Gravitational potential energy. So before I drop this slinky, that's gravitational potential energy. Okay? And then we have spring potential energy or elastic potential energy. And that's the potential of this spring to be stretched or compressed. Okay? And so this is stored energy. Potential energy is stored energy. So where else do we see stored energy besides in a slinky? We see it in chemical bonds. When we look at chemistry, it has the potential for the bond to break. Sodium chloride has the potential to break into sodium ions and chloride ions. Okay? Height. We have the ability to stand on top of the hill. We also have the ability to roll down the hill. It's stored. A toy ball has a mass of 63 joules of kinetic energy. What will be the new kinetic energy of the ball if the mass is doubled and the speed is reduced to 1/4? So let's look at the original. In the original, kinetic energy is equal to 63.0 joules. And how do we solve for kinetic energy? 1/2 mv squared. It's an object in motion. You need velocity. Okay? But then we change some parameters. The mass is doubled and the speed is reduced to 1/4. So in EK prime, we have 1/2 times 2m multiplied by 1/4 of the velocity squared. That's the modified value. Well, let's separate the numbers from the letters, from the variables. So EK prime is equal to 1/2 m. I have to square the v, so v squared. And then I'm going to multiply it by 2. And then what's 1/4 squared? 1/16. Because this piece here, 1/2 mv squared, is the same as this 1/2 mv squared. So we don't pull the half out. When I said let's separate the numbers from the variables, the half is included in the formula, not in the changed values. So then I could say then that EK prime, the modified value, this, because these are the same, 63.0 joules multiplied by 2/16. And we get what for? So 7.875. When I go back to the original question, my answer should actually be what? How many significant digits, Princess? 3. 1, 2, 3. The 5 will play on the 7. So 7.88 joules. Okay, is the new modified kinetic energy. In the second question, what is work done by gravity as a 2-kilogram pendulum moves from a height of 0.75 meters to its equilibrium position? And what you don't see is a diagram that is provided. So I'll draw it out for you. This is the ceiling. Here's the pendulum. Okay? It's going to swing to an equilibrium position, and it says that it moves from a height of 0.75 meters to its equilibrium position. If this is the floor, this is 0.75 meters. It's going to move from 0.75 meters to this equilibrium position. And then what is also told to you is that from here to here is 1.0 meters, and from here to here is 0.5 meters. And this should be like that. I didn't draw it to scale very well. Okay, so this is a picture provided to you. This pendulum weighs 2.0 kilograms. And so it's swinging down into its equilibrium is always when that pendulum is hanging straight down, when it's 100% suspended and still. Okay? So we can look at this in one of two ways. How do we solve for work? We've learned two different ways. We've learned work is equal to force times distance times the cos of theta. And we've looked at work is equal to the change in energy. We've looked at those two different ways. If we were to look at the first formula, what would be the force that we would use? We have a ball on the end of a string. What force would we use? Force of gravity. So we would say that work is equal to force gravity times distance times cos theta. Now, in this particular case, if we're looking at the first formula, we have our direction of motion here for this one is down, direction of motion. And even though it's hard to visualize, the direction of motion for this one here is also down. And so the force is going in the same direction as the direction of motion. And so what do we say about cos theta? What's our angle? When they're parallel, the force and the direction of motion are in the same direction. It's 0 degrees. And the cos of 0 degrees is 1. So cos theta is going to be 1. So we would solve this. Work is equal to mass times gravity times distance. If we were to use this formula, change in potential energy is what? How do we calculate out potential energy? How do we calculate the change in potential energy? How do we calculate the change in anything? So EPF minus EPI. Now in this particular case, which potential energy are we looking at? This should be a key word here. Which potential energy are we looking at? A ball hanging on the end of a string. How do we solve for gravitational potential energy? mgh. So work is equal to mgh final minus mgh initial. Okay? So the mass is, what's common between these two formulas? M and G. M and G, and then we could do HF minus HI. So we would have 2.0 kilograms multiplied by 9.81 meters per second squared. That's what G is. And then HF and HI. Well, at equilibrium, the final height is 0.5 meters. And initially, it's 0.75 meters. And so what would we get for a value if we were... You're probably wondering about the negative sign in work. Is this object being lifted up or lowered? Lowered. So that's where the negative sign comes into play. Okay? If we looked at this one, we can see through comparison this piece here, and then the distance that you would use here would be the change in distance from the top of swing to the base of swing of the pendulum, right? Because it's starting from here and equilibrium is straight down. So you would need the change in that distance from the 0.75 or 0.75 to the 0.5. Okay, so it ends up being the same formula. If we look at the third page, a 65 kilogram snowboarder has a speed of 2 meters per second at the start of her run. At the bottom of the hill, her speed is 15 meters per second. What was the work done in going down? So we have two pieces of information here, two ways that we can solve for work. It's asking for work. We can do work is equal to force times distance times the cos of theta, or we can do the work is equal to the change in energy. Now, can we use this particular formula? It's asking us to solve for work. We have force, which we could calculate through mass and gravity if we had to, or some version of. We could figure out the angle. Do we have a distance? No. So we can't use this formula. Distance isn't provided. So we're stuck with using work is equal to the change in energy. And so work is going to be equal to, which energy are we looking at? Kinetic. Why, Daniel? Because they're in motion. So we're going to look at EKF minus EKI. And so EK is equal to 1/2 mv squared. So we're going to have 1/2 mass times Vf squared minus 1/2 m times Vi squared. What is similar between both formulas? 1/2 mass. So we can pull those out. 1/2 m, and then in brackets, Vf squared minus Vi squared. If this is too much, pulling the 1/2 m out, there's nothing saying that you can't go 1/2 times mass times velocity final squared and 1/2 times mass times velocity initial squared. That's perfectly a-okay. That's what works for your brain. Do it that way. If this works for your brain, where you pull the light components out, then do that. It's a higher level of thinking. It's no big deal. Do what works for you. Okay? So I'm going to have 1/2 times 65 kilograms multiplied by, at the bottom of the hill, she was going 15 meters per second. And I'm going to make sure that that's squared. Minus what she started with, 2.0 meters per second. I'm going to make sure that's squared. And then I'm going to do my solving. Times 10 to the 3. What unit? Bless you. Joules. Okay, there are no practice problems for this one, but there are all of these questions for you to practice through. Okay, it starts off with a review of Science 10, just calculating MGH, just calculating 1/2 mv squared, going through those pieces. Physics 20 starts on page 187, so there's 5 of them there. If you struggle with ratio questions, like if I double the mass and I half the velocity, those are on page 180. I am going to go get your assignment, so don't leave without it.